Good afternoon. I'm Dan Freed, and it's a pleasure to welcome you back to this lecture series on the Millennium Prize problems. This is the fourth in the series of lectures that's jointly sponsored by the mathematics department here, by the CMSA, the Center of Mathematical Sciences and Applications, and also by the Clay Mathematics Institute. So today we're really happy to have our own Madhu Sudan, who will talk about P versus NP.
Great. Thank you, Dan. Thank you all for coming. 5 p.m. at the Science Center is a little late for me, but I'll try my best not to fall asleep. And please try to stay the same way if you can. Now, the existential quantifier here can mean two things. Either I'm talking about the role of the existential quantifier in mathematics, or, well, maybe, is this an existential question for mathematics as we do it today? This will touch upon both in this talk. So this talk is about proofs and computer science, computation, and this kind of a triangle between mathematics, proofs, and computing. I'll tell you a little bit about the history of this thing, talk about formalizing this question, is P equal to NP, which somehow talks, is essentially about how to find proofs, and tell you about some progress on this question, more like not so much of an update on the progress because there's lots of work and I don't expect you to go back remembering who did what in different years. Instead, to just give you a flavor of the kind of explorations that go on. And I'll talk a little bit about proofs and randomness. That item 4 shouldn't have been there, so I don't know what happened. And then maybe the future of proofs with the sort of obligatory mention of AI, because there's definitely a lot of AI in doing proofs nowadays. So the origin of proofs, this question of what is a proof is something that went back, to ancient civilizations. And here's a picture of Aristotle, who was certainly one of the many people in the early days who was trying to explore the question of what is a proof. But these early explorations were mostly based in more in philosophy than in logic, than in mathematics. And a fundamental ingredient that was missing in all of this was, can you really treat truth value of variables as an element of mathematics? That had to wait for Boole to come along. And Boole introduced this strange mathematics of zeros and ones and suddenly started doing logic with it. And there was this very interesting, in this wonderful paper, The Laws of Thought, in which he sort of relates algebra as we usually do it, factors, polynomials, in order to deduce statements about, the world of logic, and set forth this process of trying to formalize the notion of proving theorems in a mathematical language. Cantor is an early person who had an influence on this thing, who sort of foresaw some of the challenges that logic would face. He specifically did not talk about logic, but there was this underlying thing that there is self-reference and there's infinities hanging around, there has to be problems. And Hilbert finally raised this question completely explicitly, saying, oh, let's go out there and start mechanically proving everything. And this was part of the Hilbert program. I think in those days there might have even been a sense of optimism, just like we could develop a calculus and started reasoning about large parts of mathematics in an automated way or in a more algorithmic way. Maybe we can do the same thing with all of mathematics. These hopes were dashed by Godel and then Church and then finally the work of Turing, which completely settled this question in the negative. No, there is no real hope of completely settling all questions in mathematics by an algorithmic procedure. You have to have something else going on. Now, Turing's work while this is what he set out to do, had as a byproduct a minor little corollary or definition sitting out there, which was this Turing machine, which turns out to be the basis of computation today. This Turing machine allowed you to talk about any form of reasoning and computation using a finite state control. The finite state control gives you a huge amount of flexibility, but it's finite, so not infinite amount of flexibility. But with an infinite tape where you can store as much information as you want and deal with as large problems as you want. And you put them together, I'm sorry, this is what I thought you were all saying, but if you put these together, you get this amazing model of what should a computer look like. And over here, he also introduced this notion of a universal machine, one single machine that could simulate all other machines. And this is like this amazing notion. This is why the field of computer science is the way it is today. The technology is the way it is today. We buy computers because they are universal computers, and you can program them to do whatever you want to do. Turing was a postdoctoral advisee of von Neumann. Von Neumann, many years later, sort of kind of changed the names of some of these ingredients. It was a CPU and not a finite state machine. It was a RAM and not an infinite tape. But it's the same architecture, really. I mean, the coincidence is just too much to dismiss. So returning to the story of proofs, the story so far with Turing, Gödel, Church, and Turing was, well, we knew a definition of what's a proof, something that has to be mechanically verifiable. We had a notion of what's a theorem. A theorem is any statement that has a proof. And incompleteness was this unfortunate thing which says there are some statements X such that neither X nor the negation not X will find a proof in any system of logic. So this is all very interesting, very nice. What was missing was, what difference does this proof make? So here are two different proofs of a statement, T. T over here is this theorem, the statement that I want to prove. I can write down a very detailed proof, lines and lines and lines. Each line follows from the previous line by some mechanically verifiable procedure. And the last line just says T is true, and then you know that the theorem is true. Or I can just say the proof has L lines. As far as Turing, Church, and Gödel were concerned, these two are equivalent proofs. Okay? These are not equivalent to us. Why? Because they're mechanically verifiable, but it takes about L steps of verification to verify this proof. It takes some exponential in L steps to verify this one, because you have to figure out what were the intended L lines which did not fit in our margin or whatever. So why did we not put in those L lines? Well, you have to guess them and then see if it works, and if it works, that's great. If it doesn't work, well, maybe L was L plus 1. Okay? So there is a big difference between these two, and this is difference between the polynomial over here and the exponential over there is the subject of today's talk. Okay, so now we come to the P versus NP question. Where did this start? Well, this started with actually a very interesting letter that Gödel wrote to von Neumann. And in that he asked this question basically, is there an effective procedure to find a proof if one exists? So exactly the same question that we asked. I mean, why wasn't the left-hand column a proof? He's asking, could we have filled it up ourselves by some mechanical procedure? In a particular system of logic, maybe propositional logic or something, but in general, this is the question that we are interested in. And what would be effective? Maybe L squared or L cubed or something like that. Okay, these are all considered effective. So what are some very interesting realizations over here? There is this existential quantifier. There exists a proof of length L, which we want to remove. We want to say, put that proof of length L over there. You try to remove that quantifier, it costs you an exponential amount of time, at least if you do the brute force way. But that doesn't mean that there's no clever way of doing it. This is the question that we are interested in understanding. And he's asking, can you replace this exponential by a polynomial? Now, why polynomial? What's better about a polynomial than exponential? It's just intuitively more satisfactory. Just feels like we are not running through the entire space by some blind procedure. We are doing something clever. So this was the ultimate reason for why we choose polynomials as somehow acceptable and exponentials as not, but that's the way it is. Okay? And these are all some very interesting realizations already in Gödel's letter. So in some senses, this is asking the question, is P equal to NP? What was missing was any definition. There's no P, there's no NP, and there's no notion of how to say any equality. So these formal definitions took some time. Let me tell you a little bit about the steps that were needed. So first, in order to define the class P, there's a little bit of a trickiness over here, because complexity of computing a function is not something that's very easy to reason about. There's a couple of limits going on. There's an infimum over all possible algorithms, and then a limit over the data as the data size tends to infinity. And you're always supposed to think about a small algorithm and big data in reasoning about this. If you don't do this, then you can get the quantifiers wrong, and then all answers may look very different. But this is the way in which people ended up formalizing this. In particular, Cobham and Edmonds were the first people to define the class P. And Hartmanis and Stearns sort of reassured us that this is a well-defined notion. Why is this even a statement worth making? The running time of 10 times L squared, if you have an input of size L, like you're looking for a proof of length L, a running time of 10 times L squared is exactly the same as a running time of 5 times L squared. You can solve the same set of problems. How? You just use bigger algorithms. Okay? But you cannot actually shrink your running time by an exponent. So it's a very interesting definition. You are not comparing two numbers, you're comparing two functions. And when you're comparing functions, you can have an equality over here or an equivalence relation here, which does not make those two equivalent. Okay? So this is a very important realization. It is essential to define the class P. And having done this, you can now say, oh, let's look at all the problems that are solvable in polynomial time. We will be talking about only sort of yes-no questions that we can, functions that are computing yes-no values that are solvable in polynomial time, but that's a difference that's not worth stressing today. Edmonds, over here, defined the class P in order to justify a very complicated algorithm that he had found to find matchings in graphs, whatever that is. In order to justify it, he wrote a few lines of explanation saying, look, we need to justify why this very complicated algorithm is better than the brute force one that you could do with exponentially large running time. And he said, look, polynomial is a good class of functions that has certain nice properties. Let's work with that. But along the way, in one of his works, I don't know if it was the same work or not, he also actually makes an explicit conjecture that the traveling salesman problem, unlike the matching problem that he had just solved, was not going to be solvable in polynomial time. He made this conjecture in 1965, roughly. And what was it based on? He said on years of wisdom. How many years had he thought about this problem? Maybe 2 years. So he did make this conjecture that it's not solvable in P, but he pretty much laid down the footprint for how you would formalize this thing. He said we should use non-deterministic Turing machines, etc. That's the last time I'll mention that word, non-deterministic Turing machine. From now on, we'll talk about something else, but this is the class, this was a much more formal version of Gödel's question, and it was already again hinting at the P versus NP question. Still missing a definition of what is NP. That was finally defined by two researchers, Cook in the US at the time, and Levin, who was in Russia at the time, who both independently came up with this notion of the class of functions which could, the way we define NP today is the class of problems which have efficiently verifiable solutions. So there's a formal definition, but I won't go through it over here. If you want to look at the slides later and figure out what it means, you can do that. But it is the problems where if I give you a solution, it's easy for you to verify. If you want to find a solution, you might have to run through brute force search. Or you could have something efficient like Edmonds had for matching. You could find something maybe efficiently by cleverness, but at the very least, what is guaranteed is that if you have a solution, you should be able to easily verify it. What are some problems that sit like that? Well, by the way, if I ever use the word NP-complete, it stands for the hardest problems that we can find in NP. These are all problems which do have efficiently verifiable solutions, but amongst the problems where there are efficiently verifiable solutions, these are considered the hardest, and these are provably the hardest, in fact. I mean, if these turn out to be polynomial time solvable, everything in NP will be equal to P. What's interesting problems? Well, the first problem in this line was Cook's problem, complexity of theorem proving. This is the same problem that Hilbert had asked about. This is the same problem that Godel had asked about. If I give you a theorem, can you go around mechanically finding a proof? The only difference between the early version of the Hilbert question and the new version is I also specify the length of the proof. And I say, I give you a theorem and I give you a length L. Can you find me a proof which is of length at most L, if it exists? If you can solve that, then you've solved this theorem proving problem. Cook showed that this was an NP-complete problem. Levin's favorite problem, for some reason or the other, was domino tiling. He loves this problem. He just rakes it up to death. And there are lots of other problems that were shown by these two folks as being NP-complete. And Gödel's question in this language, we've already defined the class NP. On the previous page, we defined the class P. And Gödel's question is really the equivalent of is NP equal to P? Okay. So this now formalizes the question for us, and we can now go ahead and start reasoning about it. But before we start reasoning about it, let me tell you what one very important result that I've left out so far. If NP equal to P had been restricted to these kinds of problems, probably it would have hung around in the backwaters of logic, which we know is in the backwaters of mathematics altogether. So yes, it wouldn't have seen light of day. However, this amazing work of Karp came along in 72. That's kind of chronologically, you read that as being between 71 and 72, between Cook and Levin, but really these are, Levin lives in a different time scale. It was in the Russian space, and that wasn't interacting closely with the US. And probably also over there were a few years of delays between the first version and the English version and so on. So these are all contemporary works, but Karp definitely understood Cook's work and built on it. And he said that, I can use NP-completeness to suddenly explain a huge amount of algorithmic failures. We could not figure out how to do various optimization problems, logical problems, combinatorial problems, graph theoretic problems, some chip design questions. All of these turned out to be hard because they were all NP-complete. And there was just huge collection of, so there's also problems in number theory that I forgot to mention and so on. So just a remarkable set of questions that he showed to be NP-complete here. And today, if you go into this area, you'll see NP-completeness sort of transcends all forms of reasoning. There's physics, biology, economics, cryptography, law, what have you. Everything has, NP-completeness has something to say that's relevant in each one of these settings. By the way, let's take a moment at this stage. We've already seen two of the principal actors in the field of computer science. In fact, if I had to tell you about the only two important principles in computer science, these are the two: universality and irreversibility. Universality is this ability to have one computer that simulates everything else. It lies at the heart of this uncomputability result, the incompleteness of logic. Irreversibility is this option which says that if I take a function that's easy to compute, that doesn't mean that I can find pre-images of this function. And this is the underlying principle which tells you that NP-complete problems cannot be solved efficiently. And these two together are the essential tenets of computer science. These are the core axioms. The difference being uncomputability is a proven phenomenon, and NP-completeness is a suspectedly true phenomenon. We have not proved P is different from NP. That's why we have $1 million prize, and that's why I'm speaking today. All right, some NP-complete problems that you may or may not have heard about. I give you a map of some space. Find out if it's colorable with 3 colors. Okay, so can you put in colors into the regions so that adjacent regions don't have the same color? Sorry. The traveling salesman problem is another one of these sort of canonical NP-complete problems. Find a way to go through, a zillion cities, visiting each city at least once, and returning to the origin with the minimum amount of total length traversed. Okay, wonderful example of an NP-complete problem. All of these are things. There are problems like how do you fold DNA? How do you find an optimal portfolio of stocks? How do you schedule tasks? All of these translating to many other areas. Let me just mention one of my favorite problems, which is this one due to Killian. It's actually a problem that has not been, as far as I know, written about anywhere, but it's very cute. And I will not allow questions at this stage, but do read the question now. I give you three integers, a, b, and c, and I want to know if if a has a divisor between b and c. Okay, this is NP-complete. Well, there's an asterisk because it's either dependent on some assumptions and so on, but never mind. That's the question. Okay, so NP-completeness is this amazing phenomenon, and it has consequences. It has consequences to proof checking. Okay, so if you want to read a proof and verify it, there are various ways in which you can ask. Suppose you have this theorem statement T, you have this length L, and you want to know, does T have a proof of length at most L? Okay. NP-completeness gives you a completely radically different way of writing the proof than what you might normally think about. Instead of writing down a proof in whatever system of logic that you were working with, you can convert T and L into a map of some universe, and that map will have roughly some polynomial in L many regions. And if the theorem is true, then the map will be three-colorable. If it's not, it's not. So what does that mean? Well, instead of giving me a proof in your standard system of logic, you can just write down the coloring of all this L to the C regions. What colors would you want to use in each one of these L to the C regions? And as long as every pair of adjacent states regions have distinct colors, the theorem is true. If it's not, it's not. It's a very strange way of proving some things. What does it buy us? Well, it buys us a locality. The error is local. If somebody sends me a proof and says, look, it's proved, I've proved P is equal to NP, or P is not equal to NP, or whatever you want, any of the 6 problems that are still left open, well, I could just find the error. Though finding the error may take time, I can point back to it very locally and say that, look, this region was adjacent to that region and you colored them both red. That's the error. That's the end of the story. Okay? Very local way of pointing an error to you. This is possible, made possible because of the theory of NP-completeness. So this is all very nice. What can we say about is P equal to NP? I'll have more slides and more slides and more slides about this. But let's start with the first one. Okay, so that's the first line. I don't know. Nobody knows. If P were equal to NP, the cryptography as we know it might very well be impossible. We might have no options left over there. It's not completely ruled out, but we're very close to that kind of a thing. All optimization problems become easy, and you get whatever you wish. You just have to write down your wish, and it's basically any reasoning process that you want to ask, what should I hope for? Could there be a strange object that looks like this and this and this? That's the problem in NP. If you can verify an object when you see it, then we'll be able to find it because P equals NP. If P is not equal to NP, what would happen? Well, nothing dramatic will change. If somebody proves P is different from NP today, other than the fact that they'll collect $1 million in a prize, nothing changes as far as current thinking is concerned. We've been basing most of our thoughts on the assumption that P is different from NP. Most of the reasoning is built on that. We have cryptosystems that definitely, totally rely on that, and they're all going to be okay. But we might actually start becoming more the proof of P different from NP might tell us a lot more, and this is the kind of thinking stuff that I believe in pretty strongly. Okay? Now, others have been asked about this question, and by the way, there's this third option, which is that it might actually be independent. After all, it sort of originates in the same space of logic where we had undesirability, and this might well be one of those questions which is independent of the axioms. We don't know. There's even some work sort of trying to probe in that direction, and I'll talk about it a little bit later, but for the time being, yeah, it's a possibility. It's out there. Now, when the Millennium Prizes were first announced, and there's a quote from this book by Devlin which says, of all the clay problems, this one might be the one to find the shortest solution by an amateur mathematician. Okay, so I don't believe it, but that's the quote. And I think probably, if you have to prove P is different from NP, I don't necessarily feel that there has to be a short proof of this. On the other hand, if you're proving P equal to NP, it's conceivable that there's a small algorithm which does it. But there was a kind of a, this is, I don't think the next quote is in response to the first one. It was an independent quote. But this is what Lance Fortner, who writes the complexity blog, wrote there. If you show some P equal to NP, you walk away with $6 million. I think he wrote 7 then, but it was 6 today. Because you could just solve all the problems you want, because you now have an automated algorithm for proving theorems. So this is a reason why some of us might be betting that this might be the last problem to solve, as Michael just told me earlier today. So yes, of all the problems, this might be the hardest one to solve. Or we might show P is different from NP, and then, you know, nothing really, you don't collect $6 million, only $1 million. But to use the language of completeness, P equal to NP is the mathematics complete problem. This represents all of mathematics. This is the essence of what we do. All right, so on to the next stage in the talk. All right, so progress on the P versus NP question. Let's say, if there was a sort of a game going on between, you know, people saying P equal to NP on the one side, P is not equal to NP on the other side, and I'm watching, I would say, you know, the progress is the current score is 1:1. Now, what does it mean? It means I really don't know the answer. I can't predict the answer based on whatever has gone on so far. But there is a lot of progress. The game's very, very, very exciting. I'm very happy watching it. Okay, so that's my rendition of this thing. We are not going to see here is an approach that's going to work and here is an approach that's not going to work. I don't know. Okay, but why is this still interesting to us? If you have not made any progress, what could be interesting about a piece of research or a body of work and where there is no progress? Let me try to explain that. So there's two kinds of works in the area called complexity theory. This is the umbrella term which asks about, you know, limits on, you know, how easy or hard functions may be to compute. There are attempts to prove limits on algorithms. Either you specialize the algorithms or you create some spaces of reasoning where you can try to prove some results. And there's lots and lots and lots of progress over here, but these are always for special classes of algorithms. There's no general result saying all algorithms cannot do such things. So that's the thing. The other way in which P equal to NP question has influenced our research is exploration beyond the traditional question. There's been just the spirit of reductions, the spirit of equivalence of problems, the spirit of comparing if A is equal to B, then C equal to D kinds of reasonings have had huge impact on cryptography, on optimization, on randomness, on interaction, and I'll try to tell you a little bit about the flavor of all of these spaces today. So here is sort of one body of work which is in the region of, you know, let's try to separate, I mean, actually prove limits on algorithms. And in order to explain this thing, let me give you a little bit of context. P and NP we've already heard about. P space is all problems solvable with a polynomial amount of memory, not polynomial amount of time. So you could keep going over this memory again and again and again for exponential amounts of time. That would be okay. So those are the problems that we call P space. And then there is exponential time. You know, what can you solve in exponential time? Not everything. This has also been established by the work of Turing. There are some problems which are simply not computable in any amount of time, leave alone exponential time. So if you look at these classes of 4 things, they are all contained in each other. We also know that the first class here is not equal to the 4th one there. So that should immediately imply that you know, either the first one is not equal to the 3rd or the second is not equal to the 4th, right? So I mean, this is just basic logic. So we know one of those two, but we don't know which one of these two. Actually, probably what we believe is each one of these is a strict containment, but you know, can you prove at least one of these separations? And we don't know how to prove it. And this is like some of the, I mean, amazing amounts. You know, the latter separation will not tell you about the limits of NP. It will tell you that NP is not too powerful, but it's not going to say NP is different from P. But the former will certainly tell you that, you know, is a necessary step in order to show P is different from NP. If you want to show P is different from NP, you better show P is different from P space. We haven't gotten there yet. Okay. So these are wide open. There's very limited kinds of progress over here, and then finally, this past year, there's this brilliant work by Williams which makes significant progress towards this question. It doesn't resolve it, no. But you would like to say that when you have a lot of time, the amount of space that you need to simulate that much time is not as much as the time itself. That's the whole difference. I mean, the space should be much more powerful than time. And finally, he's given us a good solid separation between space and time. We would have loved to see something like logarithmic in t over here, but all we're getting is square root of t, but at least some separation over here. This is like after years and years of struggling with this question, finally we have some separation. If this number was reduced to something like t to the epsilon for all epsilon, or then we would actually have a separation P is not equal to P space. But we haven't got there. Okay? So this is one direction of progress. It's a brilliant result, very recent. Now, a second, this was somehow looking for weaker results, some things that would were implied by P is different from NP, but not the other way around. Now, what about stronger results? Actually, people have been seeking to prove stronger results as a way of proving the weaker result. One such area is the area of circuit complexity. There are many ways of describing it. The way I want to describe this area is just, remember we said the algorithm is of finite size and the problems are of large size. Now we allow the algorithms to be of about the same size as the problem. Wait, algorithms and problems are both scaling off to infinity, but there are exponentially many problems of a given size. You have to solve all of those with one algorithm which is of that polynomial size. Can we show that even with algorithms that grow with the size of the input, you cannot solve NP-complete problems with polynomial sized algorithms? Why is this an easier question to answer? I mean, clearly we are getting into the harder direction. I don't know how to show that finite sized algorithms cannot solve the problem. Now I want to show that, in order to show that, I want to say, oh, let's prove that polynomial sized algorithms cannot solve the problem. Doesn't seem like the right direction. Why look here? So it turns out now you're no longer reasoning about the running times of algorithm. You're simply you can simply reason about the size of the algorithm. This becomes a much more combinatorial kind of a question and makes it feasible for us to think more combinatorially about the problem. So it's a plausible direction, it's a fruitful direction. Have we made progress? And also actually one very nice thing that happens over here is you can actually make your measures so precise that you don't have this weird equivalence of 10 times n squared being the same as 5 times n squared. Now these are actually going to be concretely different. So you have all of these positive features, but unfortunately we've only been able to limit so what I would consider very fast parallel algorithms. This is what would be called small depth circuits for those who are familiar with that phrase. So very, very fast parallel algorithms, or algorithms that are somehow reasoning in a monotone way. And these are the things that we've been able to do, and since 80s, I would say more or less we've been kind of stuck with this question. We haven't been able to make progress. I'll come back to this question of being stuck in the next slide. It's an interesting anecdote. So by the way, this understanding why we were stuck led Rasbarov and Rudich to start asking this question, is there maybe some sort of a natural proofs barrier, some barrier that is analogous? So it's kind of an analogy to this question of maybe P versus NP is independent of the axioms. Maybe we cannot really prove this. In the way things are phrased right now, this is saying, oh, there's limits to our techniques, and that that sort of inhibits us from proving something stronger. Doesn't say that it may be independent of the axioms, but who knows, one day we might actually find that this is the path which tells us that P versus NP is somehow independent of the axioms of ZFC or something. Okay? It could be, but we don't know. But being stuck in this active world is an amazing phenomenon. I'll tell you one example. I'll use some phrases that won't make any sense to you, but just follow it all along syntactically, and it should be a fun story. So Rasburov and Smolensky in '86 proved that these fast parallel algorithms could even be endowed with something called mod P gates. What are mod P gates? I don't know what they are. They just compute sums of large collection of numbers mod 2. Okay? If you could do that very fast, then you get a class of algorithms. Even this class of algorithms will not solve some other problems, like compute the majority of n numbers or something. Okay? So they were able to reason about very powerful class of gates within the context of fast parallel algorithms, but we were stuck with mod P being prime, the P being prime. And if you try to extend this result to mod 6 gates, and 6 is not a prime, you were stuck. You could not extend this proof technique. Okay? So this is the nature of how we can get stuck in this space. So Beagle, Barrington, and Rudich tried to come up with an explanation of why we are stuck with this mod 6 computation, and they finally came up with some explanation. We roughly said something like, oh, look, if you wanted to compute some function like summation xi mod 6, and xi's are integers or zeros and ones, then you would normally, if it had been mod 5, you would have needed a degree n polynomial, but mod 6, you can get a degree square root of n polynomial. Okay, so very interesting esoteric kind of a statement. And then this was '94, and then in '99 and 2006 and 2008 and 2014, we've all been like capitalizing on this work to build amazing families of set systems, amazing collection of error correcting codes, private information retrieval schemes, and everything. So just one failure in complexity has led to all these wonderful results in diverse areas. Why? Because the questions were really somehow at the heart of our limits of what could be true and what could not. It extracted this beautiful question, a beautiful answer, and then amazing things followed. So it's just quite a I find it a very interesting story that you try to go proving something, hurt yourselves, fall down, trip, and can't find a good reason, and then in the process you realize some amazing other things. Okay, at least collectively that's what has happened in this space. All right, back to this notion of strong separations. One more strong separation that I want to talk about, and I think it is very coincidentally Kurt was asking me about this just before the talk today. There's a very interesting dual class to NP called co-NP. What is co-NP? It's all the functions which are negations of functions in NP. Well, sounds like the same thing, right? But there is a syntactic question we can ask: is this class equal to the other? And it turns out to be a very deep fundamental question, because this is asking the following question: if some theorem does not have a short proof, can you give me a short proof of this fact? Okay, so you go send out, you're a grad student, your advisor is in a mean mood, sends you out saying, look, find a proof of this fact. I know it can be proved in a page. You go there, you try out every one-page option. Okay, you manage to convince yourselves there is no solution. What do you go tell your advisor now? I tried everything, it didn't work. Yeah, well, show me your work. I cannot show you all my work. There's like, so many zillion pages of one page that I tried and none of them worked. Wouldn't it be wonderful if there was, the fact that it does not have a one-page proof also has, say, a two-page proof? That would be a consequence of NP being equal to co-NP. Okay? This is a weaker statement than P equal to NP. If P equal to NP, then NP is close under complement, because P is close under complement. But maybe this is true even if P is different from NP. So Cook, in one of the early papers, asked the question, can we try to prove NP is different from co-NP? Of course, he knows will prove P is different from NP. But it's an interesting question, and you can ask it in limited context. And proving these kinds of statements in limited context. What's a limited context? You restrict the forms of reasoning that you're allowed. You can only resolve You can only state statements of a certain type as intermediate statements and only resolve them in certain ways. Very simple logical steps are allowed. Then we can actually prove that that restricted form of NP is different from that restricted form of co-NP. Unfortunately, general purpose reasoning, we cannot prove such inequalities. That's at least as hard as proving P is different from co-NP. Okay? So these are some very interesting directions of work which are very much aligned to the question of understanding is P equal to NP or not. And by the way, I should also mention a couple of things. The reason we've been kind of so obsessed with P as the easy thing is this is what we think is tractable. These are things that you can run on computers and solve them. If I prove NP equals P, I want to say that, oh, I could start writing the theorem statements and their length and run some algorithm which will efficiently find the proof. So that's associating, conflating the notion of polynomial time algorithms with tractable ones, but this is not always the only way to think about it. On the one hand, there are people who say, well, maybe P is a strict subset of what is tractable. Why? Because there may be randomness out there, there may be quantum computing out there, and all of these may enhance my power. I can probably solve problems which are not sitting in P as we know it, but still expect to be able to run them quickly and find answers back quickly. So that leads us to the question of, is NP contained in BPP? BPP is roughly corresponds to randomized algorithms that are running in polynomial time. And we really don't know the answer to this question, so it's like a... Now, we could also go in the other direction and say that, look, is an n to the 1,000 time algorithm really a tractable one? When n equals 2, I cannot run this algorithm. So what can you do with this thing? So there are people who've very actively investigated this question of within P can we have further fine-grained refinements, and within those refinements can we try to compare how problems are relative to each other. This is another very active area of research called fine-grained complexity, and I encourage you to go take a look at it to see if there's results of interest to you. Most of these things in this latter area are kind of mimicking the kinds of things that we've done in the P versus NP world, but trying to get us to some more refined understanding of the state of interesting problems. Okay, now I want to switch gears a bit. Whoops, sorry, I'm having some. Okay, so there's one direction that I absolutely have to talk about. This is something that I've worked in, and so it's very important to me, but also something that I think is kind of one of the most fascinating byproducts of the study of P versus NP. P versus NP is the study of how to prove things. But what if you inject randomness, which is an algorithmic primitive, into this process of proving, verifying? That starts to lead to amazing collections of definitions. The first of these was exposed by the work of Goldwasser, Micali, and Rakoff, and also independently by Babai, who introduced the notion of interactive proofs. The first three, Goldwasser, Micali, Rakoff, also introduced this notion of a zero-knowledge proof. What are interactive proofs? Here are proofs in which a verifier is going to be asking questions to the prover. The prover is not a person who writes down a proof and then runs away, but sits down and waits for you to ask questions and answers them. So much more of your lecture classroom environment than reading a textbook environment. And then you can ask the question, can you verify things? And it turns out there are many interesting things that you can prove interactively where you don't know how to prove things uninteractively. Well, the simplest example that you've all seen is probably this Pepsi is different from Coke. You can give a blind taste test. And this blind taste test can be converted into a mathematical phenomenon and used to prove that graphs are not isomorphic with very short proofs. And I will not get into the details of how, but this can be done. You can actually prove that a theorem has no short proof interactively. Okay, so Kurt could ask me questions after asking me this thing, go prove this, and I say, look, I found nothing. You can ask me some questions, and I can convince you that I did not find a proof because there was no such proof. This can be proved interactively with a short proof. We don't have a classical proof. And there are many, many other things. In fact, all problems solvable in polynomial amount of space can be proved interactively in polynomial amount of time. Remarkable statements. Even more remarkable is the notion of a zero knowledge proof. These are proofs that reveal nothing about this truth of a state, about the proof, except the fact that the theorem is true. If you condition on the fact that the theorem is true, you learn nothing. And why would anybody care? This is the basis of cryptography today. Cryptography would not have gone to anywhere close to the extent that it has reached today if it were not for this concept of zero knowledge proofs and the underlying mechanics. How do you reason that something did not reveal any knowledge? What does that even mean? These amazing researchers formalized this concept, and the body of and the other researchers around them showed us how to run very, very nice zero knowledge proofs which can be used to simulate all kinds of interactions, completely general purpose in the world around us, as if there was some trusted third party who's going to be administering the protocols, but there is no trusted third party. You're just doing everything on our own. You can toss coins over the phone, you can do whatever you want, you can gamble on the internet if that's something that you like to do. Sorry. All right, another randomness anecdote is probabilistically checkable proofs. So here's two proofs for you. First one proves 2 equal to 1, the second one proves pi equal to 3. These are just two proofs that I found on the internet. So there's an error. Where is the error? Oh, if I read this line, that looks plausible. If I read that line, that looks plausible, etc. So when you look at it locally, you cannot find the error. So do proofs have to be read in its entirety? Of course, if you read from line 1 to line n, you will figure out where the bug is. But I can hide this bug by making the proof even longer. Okay, if 2 really equals 1, then you should probably read the proof even the longer proof. So do proofs have to be read in their entirety in order to be verified? And as it turns out, if you look at as you look at the proofs as we use them, as we deploy them today, yes, they have to be read in their entirety. Okay, but that doesn't mean that there doesn't exist a format for writing proofs. Recall what we said about graph coloring being used to prove things. That made it easy for us to point to errors once we found them. There are other ways of converting proofs into nice formats, and here it will be even easy for you to find the errors when you're reading it. You just read a constant number of bits, and then you'll be able to verify them. So this is a theorem called the PCP theorem that I had some role in as well, that we proved in '92, and this has been a very, very sort of a significant development in the area of complexity theory. There's just immense number of follow-up works over here with beautiful further questions and progress and methods and so on. And they have been of classical interest for one very good reason. In the past, what we saw in the works of Cook and Karp was that solving some optimization problems, like finding a traveling salesman tour which has the smallest length, is hard because it's as hard as finding proofs of theorems. That's what Cook and Karp said collectively. Now that we have these notions of probabilistically checkable proofs, you can ask the question, oh, can you give me a proof which will be accepted by this verifier with probability 99%? And even that is going to be very hard. And that says that even approximating the probability with which the verifier accepts the proof is a very hard computation. In turn, that can be converted into saying finding an approximate traveling salesman tour which is 99% close to the optimum, or sorry, which is at most 1% more than the optimum, is going to be NP complete. So this is the way in which the PCP theorem has been used, and it has completely changed radically our understanding of the world of optimization, which problems are easy and which ones are solvable. There's an entire revolution with all kinds of machinery developed about how to use PCPs to prove hardness results, at the same time getting algorithmic results to match. And There are many, the state-of-the-art variants over here are just like incredibly beautiful mathematics as well, all kinds of alphabet soups, the unique game conjectures, the sum of squares, hierarchies, and the high-dimensional expansion fields, all really, really rich domains where we can find, there's a lot of life out there. All right. Oh, one last variant that I do want to mention, in fact, coincidentally, Anand is here, who's, I'm going to mention his work in a moment. Proofs have been actually, proofs were, these interactive proofs were not first discovered by computer scientists. Apparently so this is Einstein, Podolsky, and Rosen. This is from the 30s, I guess, who somehow started challenging the axioms of quantum mechanics and realized that there was this very intriguing phenomenon that they could set up with some sort of a weird experiment where they sent two players, Alice and Bob, off to infinity, far away from each other, send some information to them, and then make it look like they were communicating instantaneously, faster than speed of light. They said, look, this is challenging the very essence of the axioms of quantum mechanics, can't possibly happen, this cannot be true. Much later, as far as I understand, this was actually experimentally validated using exactly such a setup or something very similar. And so now we can use it as a proof that quantumness actually does exist. It is a real thing. This system itself is an interactive proof in the very vein as Goldwasser, Micali, Rakoff, and Babai, with one difference: there are not just one prover, there are two provers, and they are physically separated. Other than that, this is really can be expressed in this form, and a later variant of this game can even be formalized in a very simple way. And it tells us that, look, the verifier should send the following questions to Alice and Bob, find out what the answers they give, do some computation, and if the computation works out, then you accept. And if you had no quantumness in the universe, this would be accepted with probability 3/4. If people could use entanglement as implied by the laws of physics, they should be able to accept with probability greater than 3/4, specifically 0.85. And as far as I know, this has been experimentally validated. Yes, this can be done, and it does work. Okay, so interactive proofs are all over the place. But wait, this is all physicists doing all this work. So where's complexity theory coming in? Well, complexity now can use all its machinery and mechanics. And there have been some amazing works. Mahadev showed how you can verify all of quantum computation with very simple, or at least, I don't know if it was all of, but very basic forms of quantum computation can be proven by classical verifiers using mechanics, interactive proofs along these lines. And in an even more exciting result, Anand and colleagues showed us that you can actually interactively verify all computable functions. In fact, that shouldn't, is that computable is correct, or am I even underestimating? All recursively enumerable functions. So even uncomputable ones, but as long as one direction is computable or something like that, provable. So amazing collections of results. And one of the outcomes of these protocols is like, if two players have lots of entangled bits amongst them, and they'd like to prove to you that they have it, they can send you all the bits over, okay? And that'll prove to you, or morally the equivalent of all of that, but then at the end they have no entanglement left. You can actually prove that they have n bits of entanglement using a tiny, tiny, tiny amount of communication. This is also an overestimate of the amount of communication. But yeah, I mean, really using negligible communication, you can prove that I have huge amounts of entangled bits. It's just remarkable that you can do all of these things, and these are things possible because of the tools and techniques that have been developed in the context of interactive proofs, which in turn come from the context of proofs. All right, so that's the past, or the recent past even. What about the future? So recall that, we said Hilbert's goal, well, maybe not, he didn't state it this way, but if P equals NP, we said that, you can replace all mathematicians with computers. But actually, that's already happening, some people may say, because AI is doing it. So does this now, do we have a proof that P equals NP? Okay, then how else is this LLM solving all of these problems? Okay, so That's a little bit of tongue in cheek. Firstly, this is an implication in one direction. If this is equal, then you can replace that. That's not necessary. So maybe computers will replace mathematicians, but P equal to NP as a question is intact and safe. So I can sleep peacefully. But more like, what's really happening? AI is able to prove some theorems. I mean, not all AI is solving all theorems, but there exists AIs which can prove some new theorems for which we did not have proofs in the past. But it's not like you can just say prove anything, I believe something as a short proof, go find it. It's not doing it. In fact, it's very, very far from even hinting NP equal to P. It's even further away from hinting NP equals co-NP, because you cannot ask it to prove that it's failure to you. Right? The same thing that we've mentioned all the while, that your advisor tells you to find a proof of some statement in short. You can go ask ChatGPT to prove that it was not able to there's a reason why it was not able to find a proof. You'll get a huge bill back from ChatGPT, but not an answer. Okay, so it's very, very far from doing that. But nevertheless, I find that there's something very intriguing and impressive about these interactions with AI and LLM, which also go to the essence of what theorems and proofs are to us. So all this work on NP equal to P, PCPs, and so on, we have amazing ways of writing proofs, but we don't use them on our day-to-day books. Our books do not talk about theorems and proofs. Why is it that we don't ever talk about these things? Why don't we use PCPs in all textbooks that we write? So the reason for that is, we really don't use proofs to, as in the vanilla model. There's a standard model in which we think about the logic of proofs. There's a short collection of axioms, a moderately long theorem, and a very, 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 very long proof. This is the universe that we put ourselves in when we started formulating the P versus NP question. What's the real universe that we are living in? This is a quote from a book by Lehman, Layton, and Mayer. It's the discrete mathematics for computer science course at MIT, and their notes say that some proof that 2 plus 2 equals 4 would require 20,000 steps. So obviously, we are not going to write our proofs in ZFC. Instead, we are going to use context to compress our proofs. What's context is some huge collection of axioms which we believe you know and I know. Okay, so all the facts that high school mathematics is known to you and me, and so we'll use that to make all our sentences succinct, both the theorems and the proofs. So this is the model in which we work with in the real world of theorems and proofs. This is the model that journals are employing. So what is context? I mean, what is high school mathematics? I mean, did you and I agree and sign a contract saying these are the things that you're supposed to know, these things you're not going to be expected to know? No. I mean, we make some very rough, shoddy estimation at what this is, and then we manage to somehow convince each other. But the amazing thing is these large language models are managing to reproduce the exact same kind of conversations. They're not always reliable, but they're actually, I don't know, you can put a probability on it. 10% of the times they're right. 10% of the times you're right. It's an amazing phenomenon, okay? If somebody did not know any mathematics 3 years ago, like ChatGPT did not, and now it does, it's up to the point of proving new theorems at 10% accuracy. I mean, this is just amazing, right? And it's also expressing all of its intermediate thoughts in human language as succinctly. I don't even know how to formalize this question, and it is doing it, it's practicing it. It's a remarkable phenomenon. It's something definitely that we have to watch out for. All right, so I'm almost out of time, so let me just say computing as a science, so this is the very heart of scientific inquiry. The question of P versus NP is the heart of computer science. It's the heart of scientific inquiry. And it's, always there is this thing, there's local steps. Every step of verification is a local step, but then you put them together and you get some massive, interesting object, prove some amazing theorems. And the search for proofs is the essence of all search and optimization. It's as hard as easy as, it's the core of every one of these search problems. It's a P versus NP is still open, but there are many, I mean, understanding what proofs are and what they can be is a rich area of past work but also for future work. Thank you.